Hello and good morning, friends, to another quick Python tutorial for MS365. If you just happen to fumble across this YouTube channel looking for some help with Python, specifically K-nearest neighbors today, welcome. Hopefully I can help you out. If you're in class with me, the data set that you need to follow along, the diabetes data set, is on Canvas for you. So feel free to download it and follow along. So let's just jump right in and talk about the K-nearest neighbors classifier. So let's just jump in and talk about it. So K-nearest neighbors classifier, or classifiers in general, what we're going to do with this today is we are going to create a model that, given specific predictors, will give us a class of membership. Now, in this particular case, we are trying to predict if someone has diabetes or is at risk of diabetes versus they are just have a normal diagnosis. And we're going to do that with this diabetes data set. So I've already got this data set loaded in my Google Drive. I've got Google Drive already mounted in Colab. So what we're going to want to do first is we're going to need to grab some libraries that we're going to work with. So the first library is the easy one. We know we need pandas. We need that in order to read the data frame them. Then we're going to have to grab a few other things that we've talked about in some prior videos, and then some new things from SKlearn that you wouldn't have seen yet. So let's start with the easy one. We know that we're going to do some data partitioning. So we're going to need that test train split feature from SKlearn. So we're going to grab that first. So we're going to grab our model selection test train split. So we know we need that. Okay. So there are two more things, really three more things that we're going to grab that maybe you've seen before, or maybe you haven't. So we know that we're going to use the K-nearest neighbors algorithm. We're going to create a KNN classifier. So in order to do that, we're going to grab that particular model set from SKlearn. So it's going to be sklearn.neighbors. And from that, we're going to import our KNN neighbors classifier. Okay. So just like before, where we would have grabbed sklearn linear model, and then we would grab linear regression, this time we're going to grab the neighbors set and grab the K-nearest neighbors classifier. Okay, so K neighbors classifier, we're going to pull that in. So now there are a couple other things we'll have to do that you've not seen before. We're going to have to do some pre-processing. So because the data inside this data set, which we'll see in just a second, is not using the same scale, we're going to need to normalize those numerical values. So to do that, the easiest way to do it is also using sklearn. And from sklearn, we're going to grab some pre-processing stuff. Okay, so I'm going to go into that sklearn library again, and I'm going to grab pre-processing. And from that, I'm going to import the min-max scaler. Okay, so we're going to use that to normalize our data. Now we're almost done, but on top of that, we also are going to want to grab our metrics for evaluating our model. So there's really a couple different metrics we can use. We can use precision, recall, and F1 score. To keep it simple for today, though, we're just going to talk about the accuracy score, but I will touch on why accuracy alone for a classifier is not your best move. But let's go ahead and grab sklearn.metrics. And before, if you're coming off of our linear regression video, we would have grabbed mean absolute error and mean squared error. And in this particular case, we don't want to use mean absolute error or root mean square error for a classifier. What we're going to want is our accuracy score. So accuracy score, like so. So with that, all of our data, or all of our libraries are set. We can go ahead and pull that in. Now we get to the fun part. We can go ahead and take a look at our data. So I'm going to create a data frame. I'm going to read in our diabetes data. Okay, so here is our updated data file. So I'm going to grab that. We'll read it in, and let's just explore it a little bit. Let's just take a look at it, see what we have. Okay. So we take a look, here's what we've got. Now, I am not admittedly a medical professional. I kind of got a ballpark of what all of these things are. I'm not really a subject matter expert, but what I can tell you is this is a pretty standard data set from Kaggle, and we're going to use all of these features as predictors for the outcome. And one thing I've added to make it easy for people that are getting into this in my class is that in the original data set, it's one hot encoded, the outcome. So the target here, the outcome value, the label, if you will, is one hot encoded. One meaning you have diabetes, 0 meaning you don't. I added an additional column in here saying diabetes or normal, just so you could see what would happen if you tried it with a text outcome versus a one hot encoded outcome. So 1 meaning yep, positive, 0 meaning no. Okay, so we've got all these. So we're going to use glucose, blood pressure, skin thickness, insulin, BMI, and age as particular predictors for this KNN that we're going to create, this classifier model. So the original part of this is actually not too horribly different from the way you would set up predictors for multiple regression. So I'm going to create a list or a variable, predictors, and give it a list. So I'm going to create a list of all of our possible predictors. We'll go glucose. We'll go blood pressure. If I got to spell that right. We'll go skin thickness. Interesting. I don't know how that affects you having diabetes or not, but we'll go with it. Insulin, BMI is body mass index. Excuse me. And we'll go with age. So we're going to use all of these as a starting point for our predictors, right? So as of right now, all I've done is I've created a list. So just a regular list to store all the names of the potential predictors that we're going to use, okay? So now from there, what I'm going to say is I'm going to declare another variable called x. We're going to need an x and a y here. And the x is going to be from our data frame, specifically the predictors, okay? But we also need a y, right? So that's that's our label, that's our target value that we're going to work with. So the y that we're going to need here is also from our data frame, and this is going to be, and we can use either one, but I just want to show you what happens if we use text instead. So we could use outcome here, or we could use text. So I'm going to say outcome text. Either one would work in this particular case. You couldn't do this with everything, but for this one you can. So I could choose outcome right here, or I could choose outcome text, and they would both work, okay? So at this point, I have an x and a y. If I want to check that out, if I just look at my x value, there we go, right? So it's a new data frame, and inside that data frame, or it's a piece of the data frame that's just got my predictors. If I look at it as a y, there's all of my labels, okay? So got an x, got a y, everything's looking good. So my problem though is, let's go back and look at this x for just a second. So my problem here is that all of these different predictors are on a different scale. They are not normalized. And because they're not normalized, the variance in these can cause some issues with prediction power. So we don't want to have that. We want to make sure, we want to keep these all as predictors, but we want to make sure that they're on the same scale. Because if not, the difference between the bigger and smaller values could cause more a lean in prediction power in the wrong direction than what you'd want. And a quick reminder about how KNN works, just in general, the KNN algorithm. So the way the KNN algorithm works is you set a value of k. The value of k is the number of surrounding data points that are closest by Euclidean distance to your particular observation that you're trying to classify. Euclidean distance is just a measure of the distance between 2 points. It's not horribly difficult to calculate, but the good news is you don't have to. KNN will do it for you. So before we go through that process of figuring out through Euclidean distance, the distance between your target value that you're classifying and all of the different observations inside your model, you're going to want to go through and normalize that. So that's why we pulled in this min-max scalar feature, okay? That's why we pulled in this min-max scalar. So we're going to use that to normalize our data. So I'm going to set that up. So min-max scale equals the min-max scalar function, like so. All right, so we set that up. That's step one. So the thing that's kind of weird about the pre-processing feature that's built into SKlearn, this min-max scalar, is you actually have to fit it. Not now. Don't know what that's trying to do, but let's not worry about it. You have to fit it sort of like you're training a model first. So what I need to do next, I've created that variable called min-max scale. So I'm going to go min-max scale dot fit, just like a regular model, and I'm going to fit it to x, like so. Okay. So now once I do that, I then have to actually transform my value of x data frame. Okay, so I'm going to create another variable called x norm. So this is our normalized data set, or our X norm, or our normalized value of X. Okay. And from there, I'm going to use that min max scale that I just created again. So I'm going to go min max scale dot transform. And I want to transform the value of X that we just created. So, and you know what I should have called, so I called this X norm. Nope, that's okay. We'll keep it the way it is. So now if I look at this, it's not in a data frame yet, but if I were to look at it, you'll notice that the scales have changed, right? So 0.74, 0.59, all these numbers seem to be within the same range of 0 and 1. See that? Versus before, they were much larger range of numbers, okay? So because we've normalized this, we've put them all in a normal scale between 0 and 1, it's going to give us the correct predictability based on the values that we're feeding into our model. Okay, so now at this point, they're just kind of living here in this array, and we want to put it into a data frame if we want to see how it is going to work, how it's going to look compared to what we had before. So to do that, we'll use the data frame method. So what we'll do is we'll go X norm data frame. That's what we're going to create. And we'll use pandas in the data frame method. And we'll feed it our X norm that we just created. And we'll put the value of X as our columns. So, so the rows are all of our X norm information, and our columns will be the same columns that are in the original value of X. And if we do that all correct, which it's pretty early in the morning where I'm at, it is 6:23 a.m., but I am indeed an early bird. Yep, see, I've typed something wrong. I spelled columns wrong. It's like a self-predicting prophecy, isn't it? There it is. And there it is. So here's our original data frame, or our original value of X. See that? Okay. Here are our standardized values of X, like so. Okay. So at this point, we're in a good place. Now we are at the place where we want to partition our data. But if you're interested, I can show you something kind of cool. If you're wondering how the normalization impacts your data, you'll see that if we were to plot it, like if we were to create a histogram and look at this data, the shape of the data is not going to look any different. Like the distribution will look the same, but the scale is going to be different. So let me show you what I mean. So if I go back to my original X and I look at, say, body mass index, so BMI. So if I go back to my original X and I look at my body mass index and I just plot that. So we'll do a histogram. So if you look at that, that's what this shape looks like right now. That's the distribution within the non-transformed X. So look at the scale. Look at the shape of this histogram. Now here's what I can do. Oh, you know what I didn't? I did not bring in matplotlib. So 1 second. So I'm bringing in matplotlib because I want to do a couple charts and I want to use plt show. So inside, so plt.show. So now what I can do is I can do the same thing, but I can take that X norm distribution. So I can do X norm data frame. And inside the X norm data frame, I can take my BMI column and I can plot that. So take a look. So X was my original data that had not been normalized. And if I look at the shape of it, well, it's exactly the same. Like the distribution is exactly the same. If I look at my normalized version, the distribution is exactly the same, right? Looks exactly the same, but the difference is the scale. See the scale? It's between 0 and 1. Before it was between 0 and 70 for this one, and depending on what you're looking at, it would be different, right? So it was 0 and 70 for BMI. It could be 0 and whatever the biggest number in glucose would be. Same for each one. So those scales would be different. So using this min-max scaler, it's basically normalizing this data so they're all within a range of 0 and 1. That's a good thing. We want that to happen. So at this point, the rest is pretty easy. We want to go through and partition our data. So we would do that by using that train test split feature. So what we'll do is we'll do X train and X validation, which we can call it X train, X validation, no problem. And then we can do Y train and Y validation. And from there, we will do our train test split. And we have to feed it a few things. So the first thing we're going to do is we're going to feed it our X norm data frame, right, that we just created. So we don't want to feed it X. X is our non-normalized data, right? So X is our original data set, not our normalized. So we're going to feed it X norm df. And then we're going to feed it our Y, because we don't need to do anything to that, our outcome. So now remember, because we're doing test train split, the industry standard for doing this is 80% goes into training, 20% goes into validating your data. So that's going to be the split. So we have to tell it what that test size is. Okay. So our test size is going to be 0.20, which I left off a point. There we go. Then additionally, we need to set our random state. Now, the random state here, the reason we're doing that is if we wanted to run this again, we need to make sure that when it randomly pulls the validation data, that there's equality when you let that happen. So we're going to go ahead and pull that random state data. And if you're interested, after that's over, we can take a look at XTrain and see what we have. And there we have 614 rows. This is good. And if I were to look at xval, you should see the remaining amount. There you go. So we've partitioned our data. That's looking good. Okay, so we're in a good place. So the next thing we need to do is we need to set our value of n. Okay. Now in this particular case, there's a couple ways you can do it. I'm going to just start off with an n of 5. But I will tell you that there are several different ways that you can come up with the optimal value of n. One of the easy rule of thumbs is the square root of the sample size that you have. So take the square root of however many rows of data we have, and that's one way to look at finding the best n. But for now, what I'm going to do is, because I've got two possible outcomes, diabetes or not diabetes, or diabetes or normal, I'm going to select a odd number. Okay, so what I'm going to do is I'm going to say KNN equals K neighbors classifier. And inside that, I'm going to say that my n neighbors are going to be 5. Now, you could really pick any number to start, but 5 is a good starting place. It's an odd number, which would be optimal for having two classes that we're classifying, which again is diabetes or not diabetes. But again, there's a lot of different ways that you can do this. Okay, so we've just done a K of 5 to start. Okay, K of 5. So at this point, what we want to do is we should be able to fit this model. Okay, so I could do a KNN.fit, and I'm going to fit it with my X train and my Y train, because we would do that just like a basic regression or anything else. So we'll do X train, if I could type it out this morning, and Y train. And we let it fit. If I did, look at me go. So capital KNN, Python is indeed case sensitive, KNN. There we go. All right, so we fit our model. So at this point, now it's time to actually start using it. So we're going to create our Y predicted or our Y estimates. So what we're going to do is we are going to go Y estimates equals KNN.predict, and we simply feed it our xval. All right, so that's our validation data. So when we do that, if we want to see the estimates, we can just display them after we do it. And there we go. So remember I told you the cool thing about this is you could have a numerical output or you could have an actual word-based output. So because I used, here, let's go back to the top. Because I used outcome text here instead of just regular outcome, it's actually telling me my predictions are normal, 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 and eventually diabetes. Okay. So, hey, one thing I want to touch on, and we'll get to it a little bit more later in this video, is notice that most of them are normal. there are diabetes in there, but like the majority of the predictions that you're seeing from this validation set are normal. And most likely in the original data set, they're normal as well. So these predictions are probably pretty close to right. So that's important for a reason when you deal with classifiers and you deal with the metric accuracy. We're not quite ready to talk about accuracy yet, but we're getting pretty darn close. Okay, so that's important. So if I jump down, I can use my accuracy score pretty quickly. So if I want to look at my accuracy score, I simply feed it my Y val and my Y estimates. Like so. And it tells me 75. Okay, so model's got 75% accuracy. So I want to touch on that for just a second, even though we're really not, I hadn't planned on touching on it a ton in this video. I think I might just for a minute because we've got a little bit of time. So accuracy can be a misleading metric when you're dealing with a classifier. The reason it can be a misleading metric is because accuracy is going to take the number of correct predictions and simply divide that by the total number of rows that you were predicting against. So the positive, well, I guess not a positive, the negative of that is that it doesn't really penalize or evaluate negative predictions, meaning it didn't correctly predict. It's only looking at the predictions that are correct. So if your model makes a prediction and the prediction is not correct, it doesn't do anything with it. It doesn't matter. Okay, so why would that make a difference when you're dealing with accuracy? Well, it sort of depends a little bit on what your model's doing. So for example, this is diabetes. If you're doing a random study of people and looking to see if they have diabetes, like if I were to just go outside on my college campus right now and take 100 students and sample them, most of those students would not have diabetes, statistically speaking. So if you wanted to create a model, a classifier that was accurate technically from a statistics standpoint, you simply create a model that says that nobody has diabetes, and it would be right most of the time based on just the metric score of accuracy. Okay, so just using accuracy alone is not really the best way to look at it. It's not the best way to evaluate. Now, there's other things you can do to evaluate the performance of your model. Okay, so you can do things like a confusion matrix. You can do things like precision and recall and F1 score, which are more accurate measures of how accurate your model is. So I'm going to take a second and I'll show you a couple of those. We probably won't do them in class, but in case you just happen to stumble across this, you really wouldn't want to stop at accuracy with a classifier. You'd probably want to add some additional things to it as well, just so you can truly measure how accurate your model is. And then also, I want to focus on going back in a minute here and taking a look at your value of n, but 5 is just a good place to start. So how do you go through and create a precision, recall, and F1 score report? So I'm going to go actually back up to the top. So right up here where I pulled in accuracy score from metrics, I can actually pull in something else as well. I can pull in a classification report. Okay, so I pulled in metrics, I pulled in accuracy score, so now I pulled in classification report as well. So let's go back down to the bottom and see what we can do with that classification report. So what I can do is I can go print classification report, and I then just feed it my Y val and my Y estimates, just like I would with anything else. So Y val, Y estimates, and that should be it. There we go. And when I do that, it's going to give me some new metrics that I can evaluate. So I can look at precision, I can look at recall, and I can look at F1 score. And inside that, it tells me the accuracy as well. So really the precision report, or excuse me, the classification report is a better way of measuring your performance versus just the accuracy score. So let's touch on that for just a second. So really your moneymaker here is going to be your F1 score. The F1 score is going to be a number between 0 and 1, and the closer it is to 1, the better indeed it is. So when I look at this, when I'm seeing the normal and I look at the F1 score, it's telling me that's performing pretty well. Like it's classifying people that don't have diabetes pretty darn well. And if I look at my diabetes F1 score, it's not as good. Okay, so the model is better at saying that you don't have diabetes or identifying people that don't have it versus identifying people that do. And the accuracy score does not tell me that on its own. So that's a pretty handy thing. Precision and recall, those two things on their own look at the value or the impact of the true positive or just the positives in general versus the negatives in general. So when you say positives and negatives, think true positive, false positive. Think true negative, false negative. Okay, so the positive classifications versus the negative classifications. And the F1 score is the harmonic mean of precision and recall. So good news is you don't have to do any of that math. SKlearn will do that all for you. What you want to take away from this is that the classification report is your friend. And it'll give you a little bit more detail than just the accuracy score on its own. Okay. So with that, friends, I really do hope that helps you out. I do enjoy the KNN classifier. It's pretty fun. Students tend to pick it up. The diabetes data set that I used, if you're not in class with me, it is out there. So if you go on Kaggle, you should be able to find it. I modified it a little bit by adding this outcome text to the bottom, so you may not necessarily need to do that. But outside of that, it's out there if you wanted to go out and grab it. So good luck, friends. Keep on going in your data journey. As the young people say, if this video helps you out, like and subscribe. I do this because I enjoy it, and I hope to help people out there in the real world. That's what teachers do. So with that, friends, have a great day, and we will talk to you soon.